Hello, and welcome to our video on trigonometric functions. This concerns the material in section 2.5. We'll quickly review the ideas there, which concern the values of the derivatives of the trigonometric functions, and then take a look at a couple of examples. One of these examples does a bit of preview to some material coming up in chapter 4. So on pages 155, 156 of the textbook, you saw how the definition of derivative and some trig identities could be used to derive the two differentiation formulas. One that gives us the derivative of the sine of theta with respect to theta is the cosine of theta, and the derivative of the cosine theta with respect to theta is sine minus sine theta. As a reminder, we've included those definitions. The definition of derivative is very important. We've written these in both versions. Here's the h approaches 0 form for the definition of derivative, and here is the t approaches theta form. We're going to have to work with this definition of derivative quite often in the future, so keep it in mind. But for now, we're going to just memorize these two derivative formulas. The derivative of sine theta is cosine theta. The derivative of cosine theta is sine theta. So memorize these. We'll see trig functions almost daily for the rest of the semester and all through Calc 2. So now I'm going to just look at a couple of examples to see how these results fit in with some of the differentiation results we've already learned. So let's calculate h prime of t if h of t is t squared times the quantity sine squared of t. Now recall that as you learn in trig, when you write sine squared of t, that is the way we denote taking the sine function sine of t and then squaring it. So this is a product of two functions. We have t cubed as one function, and the sine squared of t is the second, so we'll use the product rule. It says take the derivative of the first function, so that's the t cubed, we see here, then times the second function, sine squared of t, then the first function t cubed times the derivative of the second, which is here. And of course, because addition is commutative, it doesn't matter what order you do these things in. Want to take the first function times the derivative of the second first, that's fine. The t cubed is a derivative we know very well, becomes 3t squared on differentiation. As for sine squared t, we'll learn to do that in the next chapter using the chain rule. But even without the chain rule, we can still find the derivative if we realize that this is a product. So sine squared of t is equal to sine of t times sine of t, which is a product. So we can find the derivative of that last piece using the product rule again. So down here, in differentiating sine of t times sine of t, we take the first function, sine of t, differentiate it, multiply by the second, which is also sine of t, and then the first function times the derivative of the second. The derivative of sine is cosine. So we fill in the cosines for the sine derivatives, and then a little bit of algebra brings us to the final answer down here. 2t cubed sine squared of t plus, or 3t squared sine squared of t plus 2t cubed sine t cosine t. Take a look at an application problem here. So during a road test, a slow driverless car, which I know they're experimenting with nowadays, this car is programmed to drive back and forth along a straight road. At time t hours, the car is at the mile marker m of t, given by 200 plus 3t minus 6 sine t, and this is going to hold true for hour times t between 0 and 3 pi. So remember, t is in hours here. Answer two questions. For what times in this interval is the car moving backwards, that is, in the direction of decreasing mile marker numbers? And at what times is the acceleration equal to 0? So the object is moving backwards or in the direction of decreasing m, that is the mile markers are getting smaller, when the velocity is negative. So if m of t, because m of t is the position of the car, the velocity is found by differentiating m. So we have here the velocity, which we call v of t, given by m prime. So we take the derivative of 200 plus 3t minus 6 sine t. 200 is a constant, differentiates to 0. 3t differentiates to 3. And minus 6 sine t differentiates to minus 6 cosine t. This derivative has units miles per hour. Remember, m prime, by definition, it is the limit of the change in m, I'll call that delta m, divided by the change in t, delta t. M has units miles, that's the problem statement. T has unit hours, and so miles per hour, or mph. So in physical problems, remember that derivatives have units. It's important to always include those units, and the units are very easy to get. It's just the units of the output divided by the units of the input, as we see right here. Okay, velocity is negative, so we want 3 minus 6 cosine t to be negative, less than 0. And little algebra says that we must have then, we want t values which cosine t is bigger than a half. Now this is an inequality you'll learn to solve in a trig class or pre-calculus, but we're going to still take a look at a couple ways to do that. We'll first of all use the unit circle to solve this problem. And I'll add here, it helps to recall that cosine pi over 3 equals 1/2. You really have to know the values of the trig functions of the standard angles, pi over 6, pi over 4, pi over 3, 0, pi over 2, and then all those manifestations in the other quadrants. So here's the unit circle. Okay. Now in pre-calculus, you learn that trig functions can be defined using the unit circle. In particular, if we have an angle measure t, as we've shown right here, and we draw the terminal side of that angle out to this point, we know that this point has as its coordinates cosine of t, comma, sine of t. So the cosine of t is just the cosine is just the x coordinate on the unit circle. Now we've also drawn in the line x equals 1/2, and we can see that from this picture, the values we want are those values for which the x coordinate is bigger than 1/2, so we're looking for all the angles that fall over here. Now, we mentioned that cosine of pi over 3 is 1/2, so if we draw the angle from here up to this point where the line intersects the circle, this will be an angle of pi over 3. And so that'll help us come up with a way to write the solution. So what happens is this. First of all, remember we're dealing with angles between 0 and 3 pi. So we're going to be going around the circle. That's 2 pi, and even allow angles like this, 3 pi. And again, if we draw in our guidelines, here's the pi over 3 angle, and here is the other angle that intersects at x equals 1/2. We see we want, first of all, starting from 0, we can go up to pi over 3. And so all the angles from 0 to pi over 3 are going to be included, not pi over 3 because we want cosine to be bigger than 1/2. After that, over here, the cosine is less than 1/2. It flips bigger than 1/2 when we get to this angle. We've gone around the circle almost the whole way in the positive direction. We're now at the point at the angle 5 pi over 3. And when we get back up to this upper part, this upper ray will be at 7 pi over 3. And then we continue to 3 pi, and those are all the t values. So for the interval of interest, 0 to 3 pi, we have the possible t values, or the t values for which the velocity is negative right here. And of course, again, the t is measured in hours. Another approach to find the t values for which cosine t is bigger than 1/2 is to look at the standard graph of y equals cosine t for t between 0 and 3 pi, and we'll include the line y equals 1/2 in the graph. And so here it is. So again, velocity is negative when cosine t is bigger than 1/2, as we saw earlier. And on this graph, we can see that the cosine is bigger than 1/2 here and here. And not surprisingly, you're going to find this point. This corresponds to pi over 3. That's where the cosine equals 1/2. So there is our 0 to pi over 3 interval. And over here, this intersection point happens at t equals 5 pi over 3, and this one at t equals 7 pi over 3. So you can see how important it is to know those values for the elementary angles. And with that, as we mentioned, we're just looking at the places where we're above the axis or above the y equals 1/2 line here and here. And as we sketched out earlier, that happens again for t's from 0 to pi over 3. We include 0 because cosine 0 is 1. So t equals 0 is one of the values we want. We have strict inequalities everywhere else because we want cosine t to be bigger than 1/2, not equal. Part B asked about the acceleration when it is equal to 0. So previously we found the velocity function to be v of t, given by m prime, which turned out to be 3 minus 6 cosine t miles per hour. And of course, accelerations found by finding the derivative of velocity. So a of t is v prime of t, so we have to differentiate 3 minus 6 cosine t. And out of this, the 3 differentiates to 0, and the minus 6 times the derivative of cosine is minus sine of t. Gives a result there. Now notice we now have units of miles per hour squared. That's because a of t, or v prime, it is the limit of delta v, the change in v over the change in t. And remember, v had units of miles per hour. And t had units of time, which was given in hours. So miles per hour divided by hours gives us miles per hour squared. Again, the units are important here. So acceleration is 0 when 6 sine of t is 0. That's a pretty easy one to solve. We want sine of t to be 0, and for t in the interval 0 to 3 pi, this happens at times 0, pi, 2 pi, and 3 pi. Remember, sine is the y-coordinate, so the sine is 0 when your unit circle point is on the x-axis, and that corresponds to angles of 0, pi, 2 pi, 3 pi, etc. Finally, let's kind of summarize what we found here. We can kind of tell the story of this motion problem by looking at the graph of the position function m of t, and we've graphed it here. I've thrown in here the lines pi over 3, that's right here, and here's 5 pi over 3, and finally 7 pi over 3 is here. And we can see in the graph that the car starts at the mile marker 200, that's when t is 0, and it starts off by going backwards, so that's the m of t is decreasing. So the vertical axis values are getting smaller, the car is moving backwards. After pi over 3, the car moves forward. Here the m is getting bigger, so the car is moving in the direction of increasing mile markers. Then as we saw earlier, between 5 pi over 3 and 7 pi over 3, the velocity is again negative, so the car moves backward and then finishes off by moving forward till it gets to time 3 pi. Finally, let's look at the velocity function along with this. Here's the graph of the velocity function we found earlier. V of t equals 3 minus 6 cosine t in miles per hour. And here is the value pi over 3, where the velocity is turned out to be 0. And of course, the velocity, we see it's below the vertical axis here. So here is the negative part. Negative velocity means the car is going backwards and the graph is going down or decreasing. Here is positive velocity, all through here. There the car is going forward and the graph is increasing. And then finally negative velocity again between 5 pi over 3 and 7 pi over 3. The car is going backwards and m is decreasing and so forth. And so this connection we see between the sign of the derivative, negative or positive, and whether the function is going down or going up, we say decreasing or increasing is an important connection we're going to study further in Chapter 4. Okay, finally, section 3.5 concludes with a look at the derivatives of some of the other trig functions. You should be able to use the quotient rule, as done in the text, to derive the derivative for the tangent, write it as sine over cosine, and as the book shows, that comes out to be secant squared. And another example, we'll encounter the secant function now and then. Its derivative, well, think of it as 1 over cosine. And again, you could use, for example, the quotient rule or the chain rule in the next chapter. But whatever you do, the simple work with the trig identity shows this comes out to be secant times tangent. So all 6 trig functions will show up in our work. So it's a good idea to commit the 6 derivatives of the 6 trig functions to memory. Really learn them well. It'll save you a lot of time and later on, and prove to be very useful. Thank you. So let's go practice some problems on this stuff. Bye.